Akbarov and Khudaykulov, also professors Hasanov, Akbarov, Rixemboev, and I should mention that we have long-standing connections with Tashkent State University of Economics. My father, Marat Ibragimov, was professor here. My teacher is Professor Sharachmetov, who is joining us here. On our plenary speakers, one of them, prominent plenary speaker, Ruslan Salahudinov, started his academic career here at the university. We very much thank our plenary speakers for their support and for contributions to the conference. Professor Hashim Pesaran of University of Cambridge and University of Southern California, Professor Ruslan Salahudinov, whom I mentioned, Professor Ruben Unikopolov of University of Pompeu Fabra and New Economics School, John Walden of Haas School of Business, University of California, Berkeley. We're also grateful to colleagues at St. Petersburg State University, Professors Vice Dean Chernova and Professor Rubtsov. Our special thanks to Professor Sanjar Mirzaliyev, who helped us on everyday matters of organization of conference from the very beginning of the discussions on its organization here in Tashkent. We also thank our colleagues at the center, Professors Gadasina, Skrobotov, Grigoriev, Semyonov, Katya Gadasina, who helped us with organization. And we're especially grateful to students, young researchers who are joining now the conference and will present. Hopefully this event will lead to long-standing collaborations between colleagues here in Uzbekistan and abroad. And welcome to the conference. Let me now pass the word to Professor Khudaykulov, Vice Rector of International Affairs, who will talk about university and also give some particulars on our host university. Thank you.
Very good morning, and dear guests. We are extremely honored to see all of you at this university, the educational economics hub of Uzbekistan. It's a very central university in Tashkent. We are almost 100 years old. First modern economics university in Central Asia. Used to be Central Asian Economics Institute back in 30s and 40s when it was founded in 1931. It's great to see a line of prestigious representatives of prestigious universities here, and special gratitude to our distinguished guests. For instance, Dr. Hashim Pesaran. He's coming from my alma mater, University of Cambridge, and really honored to see here today. And of course, Valentina Corradi from the University of Surrey. I haven't met in person, but if you raise your hand, I would be really glad to. And Ruslan Nuruddinov, our compatriot, also one of the key persons in this conference. Dr. Ruben Enikolopov, think he's from University Pompeo. And Dr. John Walden, Haas School of Business, also present in our conference, and Dr. Victor de la Pena from Colombia, and Dr. Anton Suvorov from New Economics School. One of the important things about the conference is that it's a series of conferences. I think it's an annual conference, as I was informed, and we are privileged to be the third place to be a host of this conference. So this year's conference is, as I was informed, dedicated to the 1050th anniversary of the great Central Asian scholar and thinker Abu Rayhan Biruni, born in the city of Kath, currently Biruni, in 973. The program covers most areas of micro and macroeconomics and time series analysis, and also topics related to machine learning. And it says that the conference papers will be submitted and published in leading economic journal, indexed in Scopus and Web of Science. The topics covered in this conference will be related to crisis, economic crisis, extremes, bubbles, tail risk, structural breaks in economic and financial markets, financial dependence in economics and finance, robust econometric and statistical methods, and so on and so forth. Using this occasion, I would like to express my deep appreciation to the conference participants, our distinguished professors coming from across the world, from prestigious universities, and I would like to wish all the best to the conference work and all the success to the participants. Thank you very much, and we are really honored to see you all here. Thank you.
All right, thanks very much. Let's get started. And the next point on the agenda for today is the first plenary session. I am extremely privileged to welcome Professor Hashem Pesaran. I'll just say a few words, and actually I asked Hashem if there's anything he wants me to say to introduce him. And of course, being a very modest person, he said, keep it short. And indeed, he doesn't need introduction really. But I do want to tell you a story about Hashem. The first time I met him, it's a good story, Hashem. It's a really nice story. It's a story that I think most of the young researchers in the room would appreciate. So Hashem came to give a talk. First time I met him was in Canada. He gave a talk at McGill University. He might not remember. He gives very many talks. The problem was that the McGill did not arrange for an appropriate venue. I mean, it's an old university. It was an old hall, and the projector just didn't work. Okay? The computers just wouldn't cooperate. Okay, so there are no slides. Okay, no slides, and we tried this and that, and McGill people tried their best, and time goes, and Hashem says, okay, well, I'll have to do it on the blackboard, right? And I thought, okay, this was one of the few research seminars in the West that I'm actually going to see. presented right there on the spot from the top of the head on the blackboard. And yes, there you go. This was a paper on, if I'm not mistaken, some dynamic factor models with very elaborate matrix notation that Hashem just reproduced, out of the top of his head on the blackboard, which I thought was quite impressive. So let's welcome to the stage Professor Pesaran, who is not only modest but exceptionally effective, talented, and has made a massive contribution to econometrics. Yeah, and just to, in terms of time, we have about an hour for this session, and I'll ask Hashem to perhaps leave a few minutes for the questions. Thanks.
Thank you very much for a short but very informative comment. I'd forgotten about it, but he's right. I had to do it on a board, and I always think it's better. When I teach my own students, I always write everything on a board. However, most of them being from Far East, they take videos and pictures. So that worries me nowadays, documenting everything you do. But anyway, it's a great pleasure to be in a wonderful country and this beautiful city. I haven't had a chance yet to look around, but from what I've seen, it's just, I said, the number of cranes in a city tells you how much development is taking place. It's great. And when I was a school in Iran, I come from Shiraz, Iran, we all heard about the cities, the great cities of Samarkand and Bukhara. In fact, we have one of our famous poets, maybe you have heard of him, Hafiz, very famous poet. He says that, he's talking about this beautiful woman, and he says, this woman is so beautiful that I will give the whole city of Samarkand and Bukhara for her mall. Bekhalash Bakhsham Samarkand و Bukhara. So that always stuck in my mind. I said, gosh, when I heard from Rustam wants to invite to come here, so I have to come and see at least Samarkand, but I'm hoping to see as well. So you're really privileged to be in such a part of the world, and I appreciate to be a part of it, even for a very short time. Now, hopefully, I don't have to write anything on the board today. My presentation should show up at some stage. But let me tell you, when they are working on it to get the presentation up, what is this work about? I have been basically looking at the problem of relationships, but more focusing on the long-run relationships in my own work, while most of the microeconometricians, they do causal analysis, they will last for a long time. So that's very difficult, because you could have a policy which has a desired impact to begin with, and eventually would have no impact or even an adverse effect. And the second issue which has interested me is about what are invariant relationships in the economic system. Because we know the world is changing. Was mentioned about the structural break, was mentioned about instability, volatility, crisis. We have seen enough of them in our lifetime, even if you consider the last 20 years. And these crises are going to come and go. And therefore, we need to understand what aspects of economic relationships are actually stand up to these. And when I was a student in Cambridge, we had a great teacher, Nicholas Kaldor, some of you may have heard of. And I went to his lecture, and they were talking about, growth theory in Cambridge, and also in the other Cambridge in Massachusetts. Solow was developing the theory of the neoclassical theory of growth. John Robinson was developing the theory of accumulation of capital. And one of the issues which was quite clear, that while the world has a steady, growing, but nevertheless the ratios don't change that much. So Kaldor called them stylized facts, I remember. So he says there are a stylized fact that the ratio, capital to output, is remain reasonably constant, although both capital and output are growing if you are developing, like a steady state. So then obviously there are other ratios came in, and there is also Klein, another Nobel Prize winner, you all know, has a paper a bit later about the same time, also looked at, and he called these ratios, called them great ratios. And the question was, what is the theoretical basis of these? And secondly, whether we can look at empirical evidence for these ratios, that they are stable despite the fact the world is changing. So therefore, the problem I'm addressing today goes back a long way, and I'm sure it's going to be discussed for a number of years to come. Now, in the work I'm doing more currently, I realize that these ratios are also important in corporate finance and in finance in general. Look at the price-earning ratio, price-dividend ratio, debt-to-asset ratio. All of these are used by both people in finance and in empirical analysis as a basis of the work they do. They usually use these ratios, they explain these ratios. But unless these ratios are somehow stable, what we call stationary, or what I like to call mean reverting, because mean reversion is the key in analysis of economic system. Whether if something go out of kilt, would it come back automatically, or would it depart for a long time? If, for example, if you have a debt rising, like during the COVID, or during a war, when the debt rises, you ask yourself whether relative to GDP, like the US relative to GDP has gone up, UK has gone up, many European countries have gone up, and the question is, would they come down? And then what are the mechanisms to bring them down? So somehow, what are they mean reverting? Are there any tendency in this economic system which brings this ratio back into kind of what you may call equilibrium? So the argument for ratios, theoretically, there are many. If you look at literature in economics across the field, the sort of balanced growth models all assume the ratios are either constant. Like if you look at Barrow's work on growth, there's no stochastic thing in it. There's everything deterministic. So all the ratios in Barrow's world is constant, which obviously not true. And there are people who look at the finance arbitrage is supposed to bring back the debt to GDP or debt to asset values or price to earning or dividend to price and so on back into some kind of equilibrium. But then when you're dealing with debt, especially if you're dealing with emerging economies or countries apart from the US prints money at the moment, so that debt is not as important for the world at large. But in many countries, you cannot have your debt rise relative to your GDP. After some time, there would be solvency issues, and we have a currency crisis, and that forces you to basically reduce your debt or reduce your GDP or both, right? So that's all. So there are many mechanisms. While these mechanisms are in place, there is very little empirical evidence to support these ratios. When you look into that, you find that the evidence are quite patchy, if at all. There are people who, some people, theorists believe these ratios are all there. For example, all macro models you use, these ratios are a part of those macro models, as if they are the truth. But we know this is not the case. You'll see why in a few minutes. So there is a paper by Harding, from Australia, who says all these economic theories reject the great ratios hypothesis, but economic growth theories and macro, all the others continue to adopt them. I'm not blaming the macro people to adopt them then, because there is no way not to have these ratios stable in their model. The model blows up. You have to explain what happens if this ratio keep going down or keep going up. It doesn't make sense. So the question is, how do we bring together our understanding of the long-run relation in the economic system together with the evidence? Is it the problem with the data? Is it the problem with the econometric techniques, or is it problem with the nature of the world we live in? The answer is all the three. So I'm going to go over them and say how we're going to mitigate these issues. So these difficulties come from lack of data, as usual. Because these ratios may have a long time to operate. You need hundreds of years of data to actually analyze these ratios for each country separately. There has been new data sets available which allows us to look at this problem again. There is a data by Taylor and Jordi and someone else, I can't remember, maybe is in the next slide. Yes, that's it, Jordi, Schularik, and Taylor. They are in the University of California, Davis, and they have this macro history database which provide a long span of data, some 146 years, not for all countries, but at least for 17 countries. So what we're going to do empirically, look at this type of data in this paper, and in order to address the problem, let's stay with this slide for a few minutes, is to see what are we can then discuss some of the issues and see how we try to address it, what this paper that I'm presenting is going to contribute to resolving, or at least going towards some way resolving it. I don't think it's the end of it. I think hopefully there will be more work needs to be done. So let's start with the basic problem that if you have a ratio y divided by x, a capital Y divided by x is a ratio, y could be output and x could be capital, or could be income and consumption, or many other variables we're coming back to. I'm going to look at them. It could be long run and short run interest rate, not as a ratio, as a difference. It could be inflation and interest rate, which is topical nowadays. Again, are there any equilibrium between them? This is what most central banks think there are, but the evidence, again, is not that clear-cut. So when you look at this ratio, the best would be take a log. Of course, if you want to look at the difference, that's fine. And typically, for basically the grade ratio to hold, you need theta to be about 1 when you write in the log. So y is a log of capital Y, and little x is a log of capital X. And therefore, if the ratio has to be stable, it means that theta has to be 1, and the difference between little y and little x has to be stationary, mean reverting. Stationary is not the right word, because you don't need a stationary rate, because that's why we write I naught, because it could be possible that there are volatility in the model, so that's not stationary, but nevertheless mean reverts. So the key is whether in mean reverse. For example, if y minus x, suppose the mean of it is 0 for the sake of argument, whether it crosses 0 enough number of times. Some people have used this for unit root testing, in other words, to find out how often a variable crosses 0. If a process mean reverting, if you look at 100 years, it should cross 0 at least about 10, 20 times. But if you have hundreds of data and you cross a 0 only once, something gone wrong, right? Basically, it's not been reverting in some way. Of course, you need a more proper test for it to develop. So we were fortunate to have this long data. In fact, it is not long for all countries, and the number of countries is not very large. That's the problem. We don't have really data across many countries in the world for a long history yet. But I'm going to talk about finance later on, the more work we have been doing, which allows us to look at firms or industries. Now, what are the methods? The methods basically, I actually developed together with Youngshul Shin from York and Ron Smith, a method which is called pool mean group estimation. Let me just say a few words about this because it's related to the new development I'm going to discuss with you, share with you. Well, basically we realized at the time that to looking at these grade ratios or long-run relationships in general, you really can't have enough data for one country to do the analysis. It just doesn't possible. There are another reasons. Even if you have 140 years of data, you can't assume this grade ratio held over a whole of 140 years. You have wars, you have crises, We had COVID. So we have so many things happening over a long. The longer time you take in economics, the more problem we have about stability. So this was a fiction that we could have a long time series, in my view. So at the end of the day, we have relatively long, not long enough. However, if the idea of a grade ratio is not unique to industrial economy or developing country. In all countries, you would expect income to consumption to remain stable. So therefore, if that's the case, the theta, which I showed you, should be the same across all countries. Therefore, you can pool it, right? By pooling, you increase the, basically, precision with which you measure the theta, the long-run coefficient. So the idea of a pool mean group was the following. You want to allow the dynamics to differ across countries, because why should all countries converge to their equilibrium at the same rate? It's a fiction. Again, a lot of applied econometricians do that, especially in the US. But that's wrong, because different countries converge to their equilibrium at different rates, depending on their institution, their history, their culture, their way of looking at the world, and so on. But the long run has to be the same across all these countries. So therefore, that's the concepts of pooled. You're pooling, but mean group meaning that you allow for difference, for grouping. So you have this grouping, but you pool on the theta. So it's been very successful. There's many people. I mean, I checked last year. It's already got 911 citations just 2022. So people are using this pool mean group a lot. But there are other methods that have been developed to also pool the dynamic OLS, which is some other way of similarly allowing for short-term dynamics. There is another one, panel fully modified OLS by Pedroni. And the more recent one, there is a paper by Bretang, which builds on the work of, we have done, but allows for some extension. We're going to talk about that. So these are the methods. The question is that if these methods are there, why am I presenting a new method to you? What is wrong with these methods? Okay, so let's just go through these methods and say what the problem are with these methods and why we need more understanding of this problem. So if you can go to the next slide. Now, the problem, these methods essentially is that, as we see, obviously they need long time series, which we don't have, even with the panel. You often cannot deal with many n. In other words, the larger the n becomes, the larger t you need, because of the bias, which creates that you need to deal with the bias. But then more importantly, the method we developed, which is many people use, is what we call assume some direction of long-run causality. So for example, if you have y and x, if you run regression of y on an x, when you do the analysis, what does it mean? It means x is causing y. Not in the short run. You could allow for feedbacks in the short run, because we allow the short run to differ. But it means in the long run, it's causing. I've worked on with him, it's called long-run causing analysis. Basically, in the long run, you can have a two-way feedbacks. In other words, if y and x are out of equilibrium, is it y which is adjust to this equilibrium, or is it x adjust to this equilibrium, right? Or is it both? So when you run a y on x, what the pool mean group did, and what other methods followed, except Breitung method, which I'm going to talk about, they all deal with one-way causality assumption. Okay? So if you run a regression of y on x, it means x is causal in the long run for y. But in practice, when you look at the ratio, you don't know when the price-dividend ratio is out of kilt. You don't know, is it prices are too high or too low, or is it the dividend are too high or too low relative to each other, right? Or when you deal with income and consumption, capital and output, you don't really know the direction of causality. So we want to develop a method which allows for two-way causal long-run relationship. That's number one. The second thing you want to do, you want to develop a method which allows for some countries, for some times at least, not to be in the long-run equilibrium or near long-run equilibrium, because we have crisis, right? Different countries could go to different problems at different times, or maybe together. So we want to allow for non-cointegration. Of course, if you have one country, you have to split the time in different parts, and you say, oh, this part is okay, normal situation, it should be cointegrating. This part is crisis, that should be cointegrating. Become very complicated. We don't have enough data to actually do this kind of analysis. So what we are doing here, we want to relax the assumption that some countries may not be in equilibrium. Because when you pool, you're saying all countries are in the same state or not, right? So that's the issue. So let's just now go to the next slide. So what are the problems with these methods? Because of the finite sample problem, they have size distortion. So they often over-reject hugely. The second, the long-run causality, as I already said, is assumed to be either x to the y or y to x, while it could be both ways. The third issue, what we call episodic non-cointegration problem. So in other words, by the way, when we say cointegration, it means when y and x are cointegrated with coefficient theta equal to 1. That's what it means, right? So basically, it means that they are assuming they are in equilibrating state in all countries, which may not be true. So we want to address this. Just to show you very quickly, if you just went ahead and did some Monte Carlo, which is very simple Monte Carlo. Alpha is the coefficient of the error correction. When alpha 0, there is no cointegration. When alpha is non-zero, there are cointegration. Here it says the direction of causality essentially is from x to y, the way it's written. In this, even if you assume that all the maintained assumption of these models are correct, and then as well for heterogeneity, notice here there is some heterogeneity. Rho I is uniformly distributed between 0.3 and 0.7, and also and so on. If you look at these results, you find that, okay, the size distortion is lower for pool mean group as the sample size rises. If I raise t from 100 to 1,000, there would be no size distortion. The theory is correct in this model, right? But for the sort of sample we have, which is 150 or 200, even the method we developed under the assumption of one-way causality, under assumption that all units are cointegrating, still would not work properly, unless t is really large. The reason is because of the dynamic problem and the long run. You need to get rid of the short-run dynamics to find out what the long run is, and that's the problem. So this is if you look at directional causality, basically the problem arises is that while in theory is correct, you can run a regression of y on x or x on y, but there is no reason why if you run a regression of y on x, you get the similar theta if you run a regression of x on y, because if you run a regression of x on y, you get 1 over theta. So it doesn't follow that they would be the same in practice. So there are lots of other issues that I want to move on so we can get to the new theory and also look at some Monte Carlo and some empirical evidence quickly. So let's just go to the next slide now, please. I've already talked about episodic non-cointegration, which is basically, as I explained, that you don't think you have the number of countries that you deal, because not all countries necessarily would be in equilibrium. I'll come back to that again. If you go to the next slide, please. That is also about what I've already explained, that the theta yx need not be the same as the inverse of theta xy. However, the method we're going to develop would satisfy that, right? Basically, we want to allow for a system that it doesn't matter which way you run the regression, effectively, right? So you don't really running a regression anymore as such. So let's just now move on to the next slide, please. Okay, so let's start what is the general framework so we can see that. So we have two variables. I've simplified. You could have more than two variables, obviously, but let's just have two variables, y and x. Again, y could be the numerator and x could be the denominator, which we've taken the log of. So the equation 4 is, as most of you have seen, is called the error correcting model. And we notice here that the AYI is the fixed effect. the xi is defined by equation 6, which lagged. This is the error correction term. And delta W is just the lag changes of y and x, because W include y and x. So therefore, it's a very general setup. It allows for different short-term dynamics. Can you see? The psi IL and the phi yi, all of them for I and x are differ across I, so they are heterogeneous. Secondly, notice here that phi yi and phi xi, which are the error correcting coefficients on the xi, both of them could be non-zero. So therefore, it doesn't impose any restriction on the way the long-run causality direction is. Okay? So when you're dealing in the x causing y in the long run, is the phi xi would be zero. That's long-run causal assumption. But notice here, it's not the same as Granger non-causality, because if I have phi xi equal to zero, still delta w, which include delta y, affects x. So therefore, assuming phi being zero does not say is Granger causal. So we do allow for non-Granger causality as well as non-long-run causality. Okay? So that's the framework we want to work with. None of the methods I showed you, except Brighton, which I'm going to mention, Brighton deal with it, but it doesn't work still, is basically that this is the method we want to work with, right? So this allows for the, like say, output and capital to vary in their own way and differ across countries, and the speed of convergence could differ depending on what the phi values are. Now, in the case, please stay with the previous slide. So basically, the key is the phi coefficient, the error correction coefficient. Whether it is both zero, there's no cointegration. Whether one of them is zero and not the other one, that's the direction of causality. Now, Brighton, in a very important paper, he relaxed the assumption so that it allows for phi y and phi x both to be non-zero. But it rules out any of them being ever zero. But you know, in practice, we want both of them to be zero as well in some occasion, right? So we want non-cointegration in some period. So we want to have both being zero and non-zero at the same time, but not for the same country, but for across countries. Because you have I, right? You have I. So for some countries, it could be both zero, some countries, one of them zero, some countries, both of them non-zero. You have no idea across, when you pooling across many countries, how do you know what's going on? You need to allow for that. So it's a really complicated problem. One should not underestimate the difficulties and the requirement of the data. Let's just move on now to the second slide. So what we do, we use the what we call system pool mean group estimation. The word system is obvious. The original pool mean group estimation was published in JASA 1999, long time ago. Assume X is causal for Y. We call it system because we're dealing with no assumption about X and Y. So it's a system of equations. As likelihood function, you assume that these likelihoods are poolable, you average the likelihood. You can also deal with cross-sectional dependence later on if you want to discuss that. So then you have a vector of error correction which affects the system. If you now go to the next slide, basically the usual thing you do is nothing unusual. You write down the likelihood, you do the pool, you average across all the I from 1 to n, so it's equation 8. You stack everything, you get rid of all the short-term dynamics by filtering out all the data, and then we go to the next slide. Then you end up a nice result for equation 10, which is theta. That's what you're interested in. Notice here this theta now doesn't have the vector of phi I. The phi I is phi I y and phi I x, right? Phi I is a vector now. Notice here that it could be zero. If you look at equation 10, there are two terms. Those of you know fixed effect estimation, it looks like a fixed effect estimate. The fixed effect is more or less that. In the fixed effect, you don't have the phi in front of it, and the hi is just empty, some demeaning regression, And you don't have this getting rid of the short-run dynamics, which is delta W. Delta W is the short-run dynamics of all the variables, p order logs you put in, right? So that's the beast you need to consider and prove the theory about. Now, however, what Breitong did, it assumed that you can't have any of the phi I being 0. But as I said to you, it could be that some phi I go to 0. If some of the phi I go to 0 in here, it doesn't matter. Notice it just drops. So what does it mean when the one of the phi I go to 0? It means that country is no longer included in your sample. In other words, if you have 100 countries and 20 of them, they don't co-integrate, it's like dropping them. You don't need to know that they are dropped. The method drops them, right? As the sample size becomes larger, the phi I go to 0, it gets dropped. But it doesn't matter because I'm averaging across n. So long as you have enough countries which they are co-integrating in that period, you're okay. So therefore, non-co-integration for some of the countries has no effect on the result. It changes the convergence rate. So let me just go down. So we can easily apply this method. If you go to the next slide, please. This is just explaining that we can allow for the phi I to be 0 or non-zero. 13, when both of them are non-zero. 14, when both of them are 0. But remember, it's a vector. And therefore, we can now work out the theory. Just go forward, please, the next slide. And then basically, you can prove that the theta hat, what we call system pool mean group estimation, converges to the true value theta naught at a very good rate of root nt. T is obviously the time dimension, and root n is the square root of the number of countries in a sample. But if some of the countries are non-co-integrating, you go down, suppose pi proportion of the countries are not co-integrating, the rate of convergence, is done at the bottom of the slide, which is T multiplied by a square root of 1 minus pi n. Why this pi comes in? Because if proportion of the countries are not co-integrating, it means like dropping them from the long-run analysis. So therefore, the rate of convergence is not root n, but 1 pi n root of that. Now, of course, you cannot allow all of the countries to be non-co-integrating because pi is equal to 1 and you have no data. Okay? So it says that it's quite neat because you don't need to identify which country is co-integrating or not. It says if there are some which are non-co-integrating, so long as it's not prevalent across all of your data, which is very unlikely that happens, you will still be okay. So we have dealt with two-way causality, and we allow for non-co-integration. Okay, that's the result. Let's go on. So that's the basic eventual result of the analysis. We can also, what about the inference? The question is standard errors. As you all know, you can assume independence across countries or across time when we're doing the theory inference, but for inference you need to allow for any kind of cross-dependence that you are analyzing. Professor Ibrahim knows about it. He worked on the robust standard errors and that sort of thing. So basically, we could do the same here. So here, if the standard errors are correlated, we can now write down. If you just go back, another page, another slide. So these are sort of a bit of hairy mathematics, but shows you it can be done. So basically what you could do, you could have, can you see we have I and a J, which basically means that we can allow for cross-dependence across I and a J units. When we are coming to inference, at the stage of estimation, you don't need to worry about it. You get consistency under certain condition. So therefore, these are just show you that one could do it. Let's go to another slide. And we can also bootstrap standard errors to get rid of the over-rejection, and we do that as well, because our statistics is pivotal. Because it's pivotal, you can do bootstrap on it. What does it mean, pivotal? Basically means equation 19 is a standard normal 0, 1. So you can bootstrap from that distribution. So that's what we do. Now, it's quite interesting. There is a paper by Muller and Boston, I think Muller was one of your co-authors. I think he came to Cambridge and presented and said it's like a mean group estimation. Because what they do, they split the time, average each part, and then do the analysis on the averages. Equation 20, we also said, why don't we use their method as well to see whether there's any gain involved in that. So this, but their method requires, again, directional causality, because you have to run the regression. So none of these methods deal with two-way causality. Brighton deals with two-way causality, but unfortunately requires all of them to be co-integrating. Okay, you'll see. Let's just now go to the next page. This is the Moncala. The design is the same as what before. We are using one order lag. Can you notice quite rich? We also allow for non-co-integration in the bottom of the page. And then we choose the length of the sample for non-co-integrating to be random. In other words, which period is non-co-integrating, how long it takes. And then let's go to the next slide. And we're using, sorry, before we go to the next slide, we're using the sample size N17, 30, and so on, and then T 50, 100, and then 200. The reason we use N17 because our empirical analysis is based on 17 countries, so we wanted to know what happens as well. So just very quickly. So we deal with both situations where there's a two-way causality, one-way causality, 20% of the sample is non-co-integrating, and so on, and we allow for cross-sectional dependence, spatial autoregression, all this kind of jazz that you can do nowadays very quickly, right? So it's quite robust. So we just go to the result very quickly, and these are the results. This is when all co-integrating, and we know the direction of causality. Now, if you do bootstrap standard error, all about 94% for the pool mean group is working. System pool mean group also working, is not doing as well as the pool mean group because the assumption favors the pool mean group because we say direction of causality one way. Let's go to another page. This is the other way, but let's not carry on. Another one, and then we want to go to this one. This one now two-way causality. X, Y, can you see arrow goes both way? It's two-way causality. In the two-way causality, notice here now the pool mean group estimator. Look at the root mean square error. Even if you have 250, is 1.34, while the new estimator is 0.48. Huge difference, huge gain. And also the coverage of the pool mean group estimator is only about 50%, while the coverage of new estimator is all about 90, 93, 94%. So knowing the direction of, not knowing which way causes what, is very important in the analysis to become robust. You get a wrong inference. You get inefficient estimator and a wrong inference. So I'm criticizing pool mean group estimator. I'm one of the inventor of it. 912 people used it last year, at least cited it. But but if you had the direction of wrong and causality, you'll be all right. But we don't know. And if you go to Brighton here, pi is 0. So in other words, there is no non-co-integration. Brighton does very well as well because it allows for two-way causality, but effectively, but it's not doing as well as SMP, but it is similar. Let's go another slide. Now, no, another one, because we have no time. We want to that way. Now, this is the more general one. X and Y are two-way causality. Pi 20, it basically means 20% of the sample are non-co-integrating, correct? Look what happened to Brighton estimator. Look at the root mean square error. Shut up. Even if you have 250 observations, 6.34 won't work. Because it assumes all of the system are co-integrating because it's inverting the alpha. It divides things by the error correction term because it assumes non-zero. It really does really badly. Really badly. Okay, but if you look at the system pool mean group estimator, still it dominates all of them. So therefore the system pool mean group estimator for this kind of sample sizes, for this kind of number of n, seem to work, but doesn't mean it would work if n become very large. Because we know from the theory, t has to be larger than n. So it's another problem. We're not at the end of it. So therefore, I think it's reliable to use our data, the system Pullman group. If you just go very quickly to empirical one and then we finish. Just again, move on, please. So what we do here, we apply these methods. We apply all of these methods. I didn't mention the Muller and Watson. There are also similar problems, right? Because they assume directional causality. We're looking at the investment and GDP, imports and export, consumption and output, debt and GDP, long run and short run interest rate, inflation, long run interest rate, inflation and money growth. So there are a lot of important ratios that the world, you have to deal with: the debt, inflation, interest rate, right? So all of them are in here. Let's go there. What we do, we use all of the data, and this bracket percentage says what percentage of the years exist for this series. Because this data is not, although we say 140 years, it doesn't mean we have data on all of these variables, on all of these countries for all of the 140 years, right? It's not possible. Everything is unbalanced in this way. So just tell you what data we have available, and these are the name of the countries in the sample. Most of them are obviously advanced economies, because that's the one who have longest data. So we need to develop methods which need shorter time but large number of countries, which we don't have that yet. We don't have that method. Let's just now go to the results. So basically, one of the problems with most of this method is the long run, as I said, should be similar if you run regression of y on x and run regression of x on y and invert it, right? Only our method is invariant to it, only, because all of them have this problem, including Brighton. Let's look at the results. So these are the results for different, that's for real consumption per capita and GDP. That these bold figures is the estimate of the long run coefficient, right? It has to be about 1. Now notice here that the system Pullman group, which is SPMG, if you invert 0.907, you should get exactly 1.103. Right? I haven't done it today, but I'm sure it should be correct. But if you do the other ones, it would be similar, would not be identically inverse of each other. So therefore, but most of them, people say they are statistically significant from 1. But when I look at these numbers, I said are all right, in my opinion. That's why the difference is between a statistical analysis and understanding quantitative importance, okay? Doesn't mean all the ratios are right. Investment and GDP is the same. Now look at the imports and export is really about 1. Because you can't have your import and export different from each other forever, right? It's just not possible. Unless you are US, right? Unfortunately, that's a different, they've got monopoly, hegemony. Now if you then look at the debt to GDP, again, if you've got SMPG, it's about right. And then go further. And look at the short and long run interest rate. Oh, dead on. Look at the SMPG again, 1.01, 0.99. This is the key result. The term premium, the short and long run, is a reliable measure. In fact, most people use it to predict recession and expansion. That's reliable. But look at if you did the inflation and interest rate, there is no real link that if you raise interest rate, inflation would go down. It's just have to go together in some way, but it's not aligned at all in some way. So and if you look at the last slide about money, again, not there. There's no argument to make that inflation and money, as Friedman taught, they are aligned together. So if you then finish, basically to summarize, that there is another the slide before, but basically what we're saying that these results you need to rely on better method, allow for non-co-integration, allow for especially two-way causality, and we propose this estimator, but we need T larger than N. And there are clearly, please don't go to the next one, just wait for the previous. So if you look at the bottom, I acknowledge, always important to know what the results are limited. There are clearly room for improvement for panel co-integration to be applied to large N data set that are becoming available, which we only looked at 17 countries. It's not N not that large, okay? And then if you go finally to the last thing, and for the grade ratios, we find that for for many of them, except for inflation and money supply, the rest of the ratios, one could argue that they hold in general. Although there are some deviation, but if you use the right method, allow for non-co-integration in certain periods of the time. While it is not true that these long-run ratios hold at all time for all countries, clearly they hold on average for many countries and many time periods, I would argue, except for inflation, money supply, inflation, and short-term interest rate. I don't think those are reliable indicators, in my view. I'll stop here. If there are any questions. The whole theory of statistics is built on averages. I teach my students. The whole theory. If you understand average, you understand the statistic. The problem is heterogeneity. You know, you can't have an average of anything. So the question is, can you group them into segments? Time dependence. Central limit theorem you have learned for dependent processes. How do you prove it? In fact, I was privileged to be in Cambridge with a lot of mathematicians. I was interested in this problem of dependence over cross-section units. As you all know, I've done some work on it. And I went and talked to a guru of central limit theorem in Budapest. I was privileged. He gave me a lunch and also gave me an insight which I would want to share with you. His insight was that if you don't have order, you have no central limit theory. What it meant was that if you somehow can't segment your data such that each segment are almost uncorrelated with another segment, you can't get anywhere, right? So when you look at stationary processes, it's because you segment it here and you can drop a little bit, you go for another segment, the segment become almost independent of each other. Therefore, you go back to central limit theory. You need independence. You need homogeneity. Two things you need in life: independence and homogeneity. You have to create it for your application. There's no other way. People don't seem to understand that you can't do, all they do, all this average treatment effect. They do anything to me nowadays. Would I listen to them? Do I believe them? No. Because I don't know whether they have done the job of grouping and the job of, these groups are independent of each other. They do maybe one, not the other. So to answer your question, it's definitely a good idea for robustness. But the problem has been always in my life and in everybody's application, how the hell do we do the grouping? And how do we know these groups are independent of each other? Sorry? I have to admit, he didn't tell me like that. But he gave me a lovely lunch, and at the end of it, he says, "What is your problem?" I remember it. And when I explained to the problem, he told me, you need independence. And you need homogeneity of some form. If you look at the proofs of central limit theorems, don't rely on derivative proofs if you want to do it yourself and teach your student. Do it without looking at any work whatsoever on a blackboard without any slides. If you can do it, come and talk to me. And then you understand the statistics. So if you see what I've done here, because my co-authors are because suspicious when I tell them something. As soon as they do the Monte Carlo work, you say, oh, Hashem is right. But that's not the way. You need to understand the proofs. And I think that the work you did with Muller was very interesting because it looks at a kind of a splitting. And then, sometimes the depends not very much. So you can split the data 10 by 10 and drop 1 or 2 observations between 2 tens. You're all right. But sometimes it depends so big, you can't do it. Yeah. As you said yourself, I don't need a slide to explain something. Okay, let me explain to you the following. It's based on the new work we're doing, right? But it applies to your question. Imagine you have y and x. Why do you want to normalize? We call normalize. When you do regression, what do? You set one of the coefficient of y and x equal to 1, don't you? Let's call that normalization, right? Why normalize on y or normalize on x? Normalize on neither. How do you normalize on neither? Anderson-Rubin, 1949, when they were looking at the limited dependent variable system of equation, they had the same problem. Because they had a system of equation composed of y and x, right? They didn't have this problem, they have y and x. They also had instrument, z. I don't have a z here, right? I had no instruments in this analysis. No instrument. Did you hear me? No instrument. I only have y and x. You know how they solved the problem of this direction? They said if the coefficient of the first variable is theta 1, the coefficient of second variable theta 2, the normalization would be theta 1 squared plus theta 2 squared equal to 1. Therefore, that normalization doesn't tell you which theta 1 or theta 2 is 0 or non-zero. When you do co-integration, you say the relationship between y and x is stationary. But what does it mean? It means that it could be that one of them is a stationary variable, the other one is not. But we don't know which. Therefore, normalization is not innocuous. That's the third lesson today. Normalization is not innocuous. Just because you use the word normal, it doesn't make it normal. Language is a bad thing in life. So the way we do it now, we basically estimate theta prime w, where w is y and x. And therefore, it doesn't matter which way it goes. Okay? Because you don't allow for any of them to be 0 or 1.
Good Usually, you understand. How is it possible to apply these models in economics, in finances, and the connecting with the digital economics, i.e. systems, and the big data and others? What's possible? If you have any cases in economics, in real economics, using applicating these models with digital economics, big data, artificial intelligence, and other systems. Okay.
Let me rephrase what I understood. Often there's no point. I guess you're asking a very fundamental question, which is obviously preoccupies me too, which is, even if you know that what is the value of this research if somebody wants to do the economic policy, right? Am I not correct? This is what you had in mind? About what is the implication of that for policy? Is this right? Yeah. Okay. Now what this says that if you're dealing with a debt GDP ratio argument, or if you're dealing with income and consumption, the economies cannot persist in the long run unless they are aligned together. So basically what it's telling you, let's take debt and GDP. Again, forget about the US, I mean, because there's a separate argument for US. But for your country, for any country in the world, except for the US, you cannot allow debt to rise relative to GDP for a long time. You can allow it to rise for, like, in the short period because of a crisis, because of some wars or some situation, but you need to have policy to bring them back in line. Otherwise, it would get imposed on you. It means you cannot get away from it, right? However, when you're dealing with inflation and money, if they told you, oh, monetary policy is very, the growth of money supply is a lot and we're going to have inflation, don't believe that. That's what this says. So basically, it says that when you're dealing with debt, when you're dealing with the short and long-term interest rate, for example, you guys don't have long-term interest rate. The only country in the world that have there's 12 countries in the world have long-term interest rate. China cannot have a long-term interest rate. Even India doesn't have it. Russia doesn't have long-term interest rate because that requires a stability of a society perceived by the rest of the world for another 50 years, right? So when you're dealing with the long run, it says that in a way we have this saying, we say you cannot fool some of the people, you can fool some of the people some of the time, but not all of the people all of the time. I can say you could have deviation from long-run equilibrium, like for some of the time, but not for all of the time, right? So basically, it is possible for society to deviate from this constraint. These are constraints: solvency constraint, arbitrage constraint, balanced growth constraint, but not forever. That's what it's saying.
Okay. Well, thank you very much. We are a bit out of time, so I suggest we delay further conversation to the coffee break, and thank Hashem for the insightful talk and the life wisdom that he imparted. Thanks.
Thank you very much indeed. Thank you.